Okay, so now let's keep to develop our ideas of renormalization. And what I want to do is I want to build a rather general theory. So I want to make some statements that will generally be true. And we've been studying the theory of a scalar field. I want to make statements now that will not just hold in perturbation theory. I want them to be exact statements. And I want to make statements that will also hold even if we're not studying the scalar field. So as a consequence, so let's start off, let's say we will only use Poincare invariance. You see, this should be possible because we're trying to work out some general picture for a normalization, and we think that this will hold in any quantum field theory. So that's why this should be possible. By Poincare invariance, we mean Lorentz invariance. So what is that? That's invariance under boosts and rotations and translation invariance. Okay, so time translations and space translations. Good. And then whatever we conclude, this is not just true for scalar fields, because any quantum field theory is Poincare invariant. So it might be a theory of fermions or gauge fields or whatever. This will all be fine. Good. I also want to use, so that's the first thing that I'm going to use. The other thing I want to use is that we are dealing with a unitary theory. Okay. And if we've got a unitary theory, what does this mean? It means the Hamiltonian H is Hermitian, and it means time evolution is unitary. So these are the basic assumptions that I want to make, and nothing more than that. And in this way, I will be able to draw conclusions that are true for any quantum field theory. Draw conclusions for any quantum field theory. So we'll make statements that are generally true. Now, it doesn't matter what picture we use. Do we use the path integral or do we use operators? I'm going to swap to operators now. And you may have noticed that very often I like to build full physical intuition using the operator picture, but the path integral picture is easiest for doing calculations. Okay, so now we want to build some physical intuition. So we're going to go back now to the operator picture. Okay, so I want to introduce a state in Hilbert space. The state is going to be a Ket vector K. And what K is going to be, it will be an exact energy momentum eigenstate. Okay, so what does that mean? For example, if I took the Hamiltonian and I acted on K, I would get the energy K naught of the state. If I took the momentum and I acted on state K, I would just get some eigenvalue K, which would be the momentum of the state. And these are exact statements. Okay. I didn't tell you that this is a single particle state, and it's not necessarily a single particle state. So this could have n particles, and n could be any integer. I can take the dagger of this. If I dagger these equations, then Ket K turns into Bra K. I need to dagger my Hamiltonian because this is a unitary theory. H is equal to H dagger. And this would then just give me the energy into Bra eigenket. And the same thing for the momenta, because the momentum too is unitary. Oh, so I don't need to put the dagger in. So let's just remove the dagger. P is equal to P dagger. And this would be equal to the momentum eigenvalue times the state. Good. One of the things that I will want to do, I will want to work out what is e to the I p dot x acting on the state k. So what is p dot x? Let me just remind you, I'm sure you know, but it's the Hamiltonian times by t, so x naught, minus the momentum times by the spatial position, dotted into the spatial position. So if I act on with e to the I p dot x on this state k, all that is going to happen is the eigenvalue is going to get plugged into the exponent. Okay, and in fact, exactly the same rule holds if I was considering the bra state, because the bra is also an eigenstate of energy momentum. Okay, so I'm just recounting some facts that I expect you to be able to use. I'm going to use them freely when we proceed. Next thing is that I can boost the state. So if I take u of lambda acting on the state k, this is just going to give me the state with the momentum boosted. And the same thing is true for the bra state acting with u dagger of lambda. So I just dagger the equation above, and I'll get the bra state with a boosted momentum. Let me remind you of one other thing, the vacuum state. So naught, this is the vacuum. I'm going to assume that we have normalized our vacuum to 1. And we also know that the energy of the vacuum is 0. So let's say I've set things up so that the vacuum energy is 0. And I've set things up so that the vacuum is translation invariant. The other thing that I know is because all inertial observers agree on what the vacuum is, I know that if I boost the vacuum, well, I'm going to get back the vacuum, because the vacuum is the vacuum in any frame. So this is just using the fact that vacuum is the same state for all inertial observers. Okay. And then there's one more thing that I wanted you to remember, and that is that if I've got phi of x, I can express phi of x using the translation invariance of the theory as e to the I p dot x phi of naught e to the minus I p dot x. So go back to the earlier chapters and we discussed all of these facts. Good. Okay. So what do I want to do with this? Well, I want to do the following. In fact, let me do one more thing. You know how the field phi of x transforms under a Lorentz transformation. This is again something that we dealt with in one of the earlier chapters. This is also something that we're going to use. So in particular, if you set x is equal to 0, then u dagger phi of naught u of lambda is equal to phi of naught. Good. Okay. Now let's try to derive something. So I want to study this matrix element, the state k, phi of x, and the state naught. So now I'm going to use the fact that we can write phi of x as in this green box. And what do we get? We'll get k e to the I p dot x phi of naught e to the minus I p dot x. And there's the vacuum. And then, as we've just said, e to the I p dot x acting on bra k just plugs in the eigenvalue. So we'll get e to the ik dot x, state k, phi of naught. And then acting on the vacuum, we just plug in the eigenvalue. All of the energies and momenta are 0, and e to the naught is 1. So that e to the minus ip dot x just becomes 1. Good. And then because phi of naught is equal to u dagger of lambda phi of naught u of lambda acting on naught. So that equality follows. And then I know how u dagger of lambda acts on bra k. It just Lorentz transforms that momentum. Here's phi of naught. And u of lambda on the vacuum gives me back the vacuum again. Good. We'll continue in a moment.